Okay, so in question 16 of the exam 1 review, looking at a bit of a throwback question to the scaling tutorial from 114. We're looking at the earthworms absorbing oxygen through their skin. So we're given a lot of information on the makeup of the worm, how to treat, modeling as a cylinder with no end caps. Assume the worm has 90% of its surface area in contact with the air. We're given the concentration of the molecules, thickness of the skin, and the key thing is looking for the rate of transfer of oxygen molecules. So this is a Fick's law question, Fick's law diffusion question, written in the context of the sort of breathing worms tutorial in 114. So it's Fick's law. So we have the number of molecules per unit time, so that's the quantity we're looking for. It's given as D times A times the change in concentration. So D is the diffusion constant, A is the cross-sectional area, delta C is the difference in concentration between 2 points, and then we have L here, which represents the distance which these molecules have to travel through. This one's slightly challenging to think about this A and the L in this particular question, because this A is actually going to, so it is a cross-section area, but it will actually represent the surface area. I'll explain that in a second. And L here, the length, will actually represent the thickness of the worm's skin. So I'll try to draw a picture down here, maybe a couple of pictures. So this is the ground, and I have my cylinder on the ground, and 90% of it is in contact with the air. The other 10% is in contact with the ground. And we assume there's no diffusion at that point. So the oxygen molecules are going to basically diffuse through the skin. So in this sense, the cross-sectional area through which they would diffuse is the same as 90% of the surface area of the worm, if we exclude the area of the end caps. So that's might have been easier to state that exclude the area of the end caps. I'm guessing with this particular dimensions of the worm, the end caps will comprise a very small volume either way. So that's when, in a sense, this is where this cross-sectional area here is actually it's coinciding with the surface area of the worm that's in contact with the air. So the surface area of a cylinder, sort of the outside, the curved sort of portion of the cylinder, is the same as that of a rectangle, where the edges here are given as the circumference is 2 pi times r, which is equivalent to pi times d, which in our question is pi times w, because this cross-sectional width is meant to indicate the diameter. Times then, so that will be these are equivalent, times then the length of the worm. And yeah, so we have, in a sense, the width. You could use 2 pi r by divided by 2, or just use the same, just use a w, that's pi times d. So I'll do that down here, since we have a lot of quantities to place in our equation. So if you do pi times the w up here times L, which should end up with an area of 2.41 by 10 to the minus 3 square meters. So that's using pi, w, make sure you convert to meters, so 0.64 by 10 to the minus 2, or 0.0064, and L here is 0.12 meters. So everything should be in meters. Okay, then I'll just draw a separate picture, sort of as a subsection of the skin. Okay, I'll have enough room down here to show you what this L represents. So the L in this equation here represents the thickness through which or the distance which the molecules have to travel. So on this side we have the 5.26 by 10 to the 24 concentration. Inside the skin is 3.1 by 10 to the 24. So the molecules are sort of diffusing through a distance of 1 millimeter. So this L here, and the thickness is not the same thing as the length of the worm. And just be careful when you're sort of defining those quantities. Okay, so we can see where else do we need. So we have the diffusion constant, that's given. The area we just solved for through knowing the length of the worm and its width. The change in concentration we can solve from the two concentration values. And what we need to remember, we have the thickness as well of this L, the 1 millimeter, and we not to forget about the 90% of the surface area. So my N over delta T will be my diffusion constant, 2.3 by 10 to the minus 9 meters squared per second, 0.9 for the 90% of the area, which is down here, 2.41, 10 to the minus 3 meters squared. The change in concentration, 5.26 by 10 to the 24 minus 3.1 by 10 to the 24 is 2.16 by 10 to the 24 molecules per cubic meter. So we're running out of room here. And then divide it by the thickness through the length through which they have to diffuse, which is 1 by 10 to the minus 3 meters. So, if you get all your numbers correct, this should work out to be 1.08 by 10 to the 16, I believe. Just double check. 10 to the 16 molecules per second. So, oxygen is a diatomic molecule, O2. So let's zoom in here on those numbers so you can see them a little clearer. Yeah, so the difficult part here is probably getting the area, or figuring out the cross-sectional area, which is sort of coincides with the surface area for this problem. And yeah, everything else is sort of given, just making sure you get all of your unit conversions correct.